Hello, everyone. So different setup today. Um, Let me just check that everything's working first of all. But I think everything's all right. Can you hear me? Yeah. Okay. Cool. Good. Good to know. Thank you very much. All right. Cool. That's all fine then. Okay. Yeah. So slightly different setup today. Just not feeling too crash hot, so didn't think I'd be up for standing for 2 hours. Yeah. For what it's worth, I do have the document camera should we need to demonstrate anything, but I think today might have pretty limited use of that. The graphics in the slide should be enough for the most part. Alright, we'll give people another couple of minutes to show up, but to start off, some housekeeping. So, where are we at? So today's lecture 3. We're doing Divide and Conquer. We're doing the first part of this lecture. The second part of this set of slides will be done tomorrow. So that's lectures 3 and 4 are in these slides, and these slides are on Moodle. By the way, it's come to my attention that some students have their Moodle notifications turned off, which means that you're not getting the announcements on Moodle. All I can say is, you're doing a Moodle course, you should probably have your Moodle notifications on. So if you've not got emails from the Moodle announcements, then that's something to look into. Assignment 1 is due next week. Question 3 has been changed. It was changed on Saturday, I believe. So please make sure that you're aware of the new question 3. We should have we should have an FAQ thread going up on the Ed forum shortly. That FAQ thread will have all the commonly asked questions on the forum so that you can see them all in one place. And we'll publish a link to that on Moodle so that you can check that out. Again, everyone should have Ed access. I sent out a Moodle announcement this morning reminding you of the link to join the Ed forum. If you've not done so already, then please sign up there. Toaka asks, are we expected to complete all of the tutorial questions every week? You're adults, you can do as many or as few as you want. But with that said, I don't think completing them all is necessary in all circumstances. It depends on how easy or difficult you find them. They will kind of slow down a bit. So the set of tutorial questions coming out for Divide and Conquer, I'm hoping to have those up either tonight or tomorrow. Most likely tomorrow. That tutorial set 2 covers lectures 3 and 4, but it only has 13 questions, I think 13 or 14. So it should be a smaller set. Tutorial 1 is larger because it covers a larger set of techniques, because it includes all your data structures and so on that you've seen in previous courses, as well as just general ad hoc problem solving. The subsequent tutorial sets are both smaller and they come out less frequently. So for the first couple of weeks, there will be a tutorial set basically every time that we start a new topic. So that is lectures 3, 5, 8, and 11 off the top of my head. So they will start to space out a bit as we go. And again, they will be shorter. Highly recommended tutorial problems. Yeah, that's what the K questions are for. So we've marked all the questions as either K or H in the tutorial sets. We recommend that you attempt all the K questions. Attempt doesn't necessarily mean sit there and think about it for a whole day. If you can't get it quickly, then you may wish to just read the solution, or better yet, come to the help session where we're discussing that problem. Yeah. So all the K questions should be covered in at least one of the recorded Zoom sessions. And then in addition, we've got some face-to-face help sessions. So hopefully you've all received notification about the Tuesday and Friday afternoon help sessions. Those will be in person. So from now on, Tuesday and Friday afternoon help sessions at 5 o'clock will be held in UNSW Business School Level 2, Room 215. And so if you've not, that's a good way, especially obviously if you're in Sydney, to come and have to chat to Frank or Gerald and work on some problems together with other students. Request any problems that you'd like to see solved by a tutor. And so, that's a good way to practice your problem solving skills. In addition, come along to the online sessions when you're able to. I would recommend that for most students, you probably should come along to at least one or two of those during the week, depending on, of course, your availability. You may wish to watch recordings of some instead. But definitely you should strongly consider coming along to at least one or two of those. Okay. KA, not the face-to-face ones, not exactly like the online ones. We're kind of experimenting with the format because it is new. We've not run these help sessions face-to-face before, so we're trying out a couple of different things. But we're gonna try a more like flipped classroom approach tomorrow. So Gerald will be splitting you guys up into small groups to work on some problems together, and he'll facilitate. 2 questions will come out for every new topic, so not necessarily every week, although for the first 3 or 4 weeks there will be one every week, and then it slows down after that. There'll only be 2 more from week 6 and possibly 8, I think. Yeah. Okay, so again, read the tutorial problems, attempt most of the K questions if you're able to, and make sure that you understand the solutions to the K questions. All right, so that covers assignment, tutorial problems. I think that's pretty much everything. Is there anything else I had to talk about? Not really. I guess consultation, Tuesday and Friday, 2 p.m. There's consultation. People haven't shown up so far, so that's okay if you're understanding everything, but if you would like a way to ask me questions directly, consult is the best time to do it at 2 p.m. at 2 p.m. on Tuesday and Fridays. Okay, I think it's time to get started on some new content. So we're just working on the 6th set. All right, let's get started. So we're going to start with a couple of problems that hopefully give you some motivation for the method that we're trying to use, which is divide and conquer. So we're going to start with a puzzle that maybe some of you might be familiar with. You have 27 coins. They are all identical with the exception of one counterfeit coin. That counterfeit coin is lighter than the other 26 coins. And so you have a pan balance, which is you can weigh a subset of coins against another subset of coins to see which side is heavier. And you can use this only 3 times. Your task is to find the counterfeit coin. Let's get some suggestions from the chat. How would you do this? So when I say pan balance, I mean what I mean is we have this kind of setup, I can put some stuff in pile A, and I can put some stuff in pile B, and whichever one is heavier will drop, and whichever one is light, whichever side is lighter, that will rise. So we've got a couple of different suggestions, which is good. Yeah, 27 is a bit of a hint. But I want to start with the other suggestion from, I think, Google Fang, as well as Tuaka, which is to split into 13, 13, and 1. Let's take out one coin from the pile and weigh 13 against 13. I'll come back to the other suggestion later. If we weigh some 13 against another 13, what are the possible outcomes? What are the outcomes if I have 13 on each side? They could be equal, in which case we're very happy, right? If they're equal, then the last coin remaining is the fake. Certainly, yeah, if they're the same, exactly. The one that was left out of this weighing has to be the only one that's lighter than anything else. However, we do have a problem if, we still have more work to do if they're unequal. If unequal, then I can say that whichever is lighter of these two sets of 13, that must contain the counterfeit. Which means that after one weighing, I've narrowed it down, in the worst case, from 27 to 13. And now it seems sensible to recurse, that is, apply the same method to this remaining set of 13. Leave one out, weigh 6 against 6. So after the first weighing, I've got, at the start I've got 27. After one weighing, I may have 13 remaining to search from. And after the second iteration of this same idea, I go down to 6. But if you have 6 coins, and you only have one weighing remaining, that's going to be insufficient, right? You certainly can't get from 6 coins to which one is the fake in just one weighing. So, unfortunately, this way is no good. If you were to weigh the half and half out of this 6, you'd be left with 3 coins, and any one of those 3 could be the counterfeit. So, there's some discussion of this, but 13 and 13 is not the right idea. In essence, we're hoping for a bit too much with our best case. Like, we're making the best case in such a way that it would immediately solve the problem, but it's quite rare. Whereas, as a few people are suggesting, if we put 9 coins into the pile on the side, then that still gives us some work to do in the best case, but it means that we're winnowing down the search space much faster. So let's have a go at the other way, which is to divide the pile into thirds rather than halves. So in this situation, I have 9 coins on one side, 9 coins on another side, and a third pile of 9 coins elsewhere. I'll call these piles A, B, and C. Why is this out of focus? Don't remember the buttons. Okay. So, what we're going to again ask is, what happens if they're equal? What happens if they're unequal? If they're equal, then C has the fake. Certainly, if piles A and B are equal in weight, then neither of them can have the counterfeit coin, so C must have it. But if they're unequal, then the lighter of the two piles has the fake. And so after one weighing, in any case, even in the worst case, we've narrowed it down from a pile of 27 to a pile of 9. That's divided the search space by 1/3. And so at this point, it should hopefully be clear that you should repeat this. Again, take the pile of 9 and divide it into 3 and 3. And then into, with 3 on the side. And whichever of these three contains whichever of these piles of 3 contains the counterfeit, again, you can decompose that into 3 piles of 1, from which you can determine the counterfeit. So in the first weighing, we've gone from 27 down to 9. In the second weighing, we've gone from 9 down to 3. And the third one goes from 3 down to 1, and we are done. Andrew, for each triplets, aren't you measuring them twice? No, we're not actually weighing 9B against 9C. We only weigh 9A against 9B. And so if they're equal, then we don't need to compare C against anything. We know that C has the fake. Yeah. And again, this is, there are variations of this problem where it might say a counterfeit coin has a different weight to the other coins, in which case this wouldn't work anymore, right? Because if it's just different as opposed to strictly lighter, then we can't determine which of pile A or pile B has the counterfeit, right? But since it says the fake is strictly lighter than the others, then we can narrow it down by 1/3 at each time. So as we've discussed, divide into 3 groups of 9, weigh group A against group B. Whichever group is lighter has the fake. Otherwise, if they're both equal, then C has the fake. And now we've narrowed it down to a problem of searching 3 groups of 3 and then 3 groups of 1. Let's switch back to the slides now. Okay. Hopefully, again, easy enough to understand, but also an important idea, which is if I have a large problem, maybe I can break it down into one or more smaller problems of the same structure. And so this method is called divide and conquer. We've already seen one application of divide and conquer, which was merge sort. To merge sort a big array, you break it into the first half, the second half, and merge sort each of them, and then merge them together. Which is exactly what we've talked about here. And so we're now going to look at another application of this idea, which is to count the inversions in an array. Which again, we're going to define shortly. So again, to give you an idea of where this might be useful before we actually define the problem, maybe we're making some kind of recommender system for movies. This is one way that you could design some kind of Netflix algorithm, say, which says, if you like this, users like you like users with similar preferences to you like these other movies, right? So in order to do this, one building block is to say, for any pair of users A and B, we need to have some sense in which we can measure, are their preferences similar or not? Yeah. If person A has ranked a bunch of movies and person B has ranked a bunch of the same movies, then one way of doing this is to say, let's call these movies by B's choices, and index A's list by AI. So I'll show you what I mean by this. Say I have person B's list, and I'm going to label the movies 1, 2, 3 according to their position in B's list. So always the position of movie I in B's list is the ith preference. Then I'm going to index, so I'm going to label array A, that is person A's preferences, in the same scheme. So person A also likes movie 1. Their next favorite movie is movie 5, which was by definition B's fifth preference. A's third preference is movie 9, which again by definition was B's ninth preference, and so on. And so the array that I'm having is kind of reverse index to how you might think of it. We're going to think of A of 9 as being 3. So A asks, what is the position of B's ninth favorite movie in A's list? Okay. It's not exactly like a hash table in that a hash table is for jamming a large set into a small set of indices. So this doesn't exactly do the same thing, but so be it. Yeah, a dictionary is just like a hash table is one way to implement a dictionary, so that also doesn't really narrow it down. All I have is like the array B is kind of the way it is by definition. It's simply the array 1 through n. Array A is A's ranking of those same movies, and again for each movie I, B's ranking of movie I is I itself. A's ranking of movie I is the ranking AI. So movie 9, which is by definition B's ninth favorite movie, will be A's third favorite movie, and so on. Now, what are ways in which you could look at this pair of arrays, that is, this pair of A and B's movie rankings, and how could you determine some degree of similarity between the two people? So I think a very crude way of doing this would be to say, oh, do they have the same favorite movie? Just look at the first entry. If they're equal, then we say that they both like the same movie, and therefore there's similar users. This obviously loses a lot of information, right? Why bother getting them to rank everything if we're only caring about their first preference? But it is a way. The 9 in A of 9 represents the movie. The 3 is the ranking. So movie 9 is A's third preference. Yeah, the movie name and index is the same in B, but of course A has a different order. Yeah, so there's some more complicated ideas suggested by Blake and Hussein, more complicated than what we're going to do. Yeah, so we can look at the distance between. So how to put it? We can go over each movie and ask, okay, B ranked you 9th, but A ranked you 3rd. That's a difference of 6 in the preferences, and we are going to like that's somehow going to contribute towards the total. Maybe we add overall movies, or we take a max, or something like that. The question is not to produce A from these two arrays. That's straightforward enough. I haven't actually told you what the question is, but we're still discussing what are kind of sensible ways to look at these two arrays and measure how similar the two lists are. Now, B of 9, yeah, sure. If we were to use the same notation for array B, then B of 9 would be 9, and that's the definition of like movie 9 of the indexing movie 9. Okay. So yeah, these are Blake's and Hussein's suggestions are useful and very viable ways of doing this. But we're going to go with a slightly different approach, which is to say, let's count not over each individual movie, but How many times they disagree? Yeah. How many times they disagree is an interesting one. It's certainly something that makes use of all the information, which is better than the first preference way I suggested. But there's a bit of a, there's a bit of a hiccup there, right? In the sense that two lists can be very similar, but have just one, have very few points where they agree. So, actually, for an example, so I like William's suggestion because it's interesting. If I have the lists, say B likes movies 1, 2, 3, and 4, and A likes movies. Actually, let's give them a couple more. Say A likes movies 1, 5, 3, 2, 4. Whereas C likes movies 6, 1, 2, 3, 4, 5. Now, A and B agree in two places. They agree on their first and third favorite movies, but they're quite different on many of the others. Whereas movie 6 was C's favorite, and otherwise they completely agree with B. So there's a question of whether A or C is more similar to B. And I think you could make a good argument that a system that only counts the number of shared preferences, which gives A and B a score of 2, but C and B a score of 0, doesn't fully account for how similar they are. And maybe that alone isn't really... how to put it? Maybe that alone isn't really capturing all the information. One thing that I could say about arrays, about people B and C, is that for many of the pairs of movies, they rank them in the same order. Yeah. If I take movies 2 and 4, if I take movies 2 and 5, B and C both prefer movie 2 to movie 5, but A prefers movie 5 to movie 2. And if you look through, there are actually a lot of pairs where A ranks them in the other way around to how B and C rank them, whereas B and C only disagree on 5 of the pairs. They disagree on everything involving movie 6, right? Let me just take some questions. Yeah, so Jordan, we want to find some kind of measurement of how different the two lists are. I'm going to suggest one way of doing it. It's not the definitive best way to do it, and we're not even going to argue as to whether it's mathematically optimal according to any particular criterion. It's just one suggestion. Yeah, so Lance, this is what we're going to do. Blake, that's an interesting idea. Keep that in mind. Yeah, the number of swaps required to make them the same would be the number of swaps required to sort array A. And that's an interesting problem in and of itself. William, this never happens. We defined the movies by B's preferences. So B's favorite movie is definitionally movie 1. Yeah? So B never likes movie 2 better than 1. That's against the definition. Okay. Let's return to the slides. Again, this is all for some context. We're going to lose a lot of the background, like in terms of movies, and just deal with a bare array shortly. Yeah, counting the number of times they disagree by looking at when their preferences are swapped. Yes, that's pretty much exactly what we're going to do. Hussein, yeah, the issue with your suggestion is that if we have n movies, then your matrix will be n by n, and so that n squared way of computing that matrix, because you'll have to fill in every entry of the array, turns out to be slower than the best we can do. We can encode the same information without filling in that array, that matrix in full. So that's our task. All right. So, yeah, as we've discussed, one way of measuring the difference between these two users, not the only way at all, and not necessarily optimal according to any, criterion that you might want, is to count how many pairs of movies are out of order between them. So we're going to say an inversion is a pair of movies, I and J, where I is less than J, that is, B prefers movie I to movie J, but A prefers movie J, that is, they put AJ at a lower index preference, so higher up on the list, than they do movie I. So I is less than J, but the ranking AI is greater than ranking AJ. Greater meaning in higher number preference, and so it's not preferred. Okay. Hopefully, it's clear that this is. Oh, I've just realized something. All right, that doesn't matter. Okay. Yeah. Never mind. So let's have a look at some examples. Let's look at the gold and the red pair. So movies 1 and 2. By definition, B prefers movie 1 to movie 2. And A also prefers movie 1 to movie 2. Which means that movie 1 and 2 do not form an inversion. They're in the same they're in the same order in both lists. On the other hand, movies 4 and 7 do form an inversion. They're in positions 4 and 7 respectively on B's list by definition. But on A's list, they're in positions 8 and 5. And that's out of order. Yeah. So this is what we're going to do. We're going to go over all pairs of movies, and we're going to count how many pairs are out of order, like 4 and 7 here, rather than like 1 and 2. Make sense? So, of course, you can, if there are n movies, you can just go over all the pairs. So, go over all pairs of movie I and movie J, and add 1 to the total if they're out of order. If A ranks movie J better than movie I. But of course, since you're going over all movies I, all later movies J, this takes quadratic time. It takes 2 nested loops of n items, so that is n squared time. But we're going to do better. We're going to actually get this down to n log n time by applying divide and conquer. Okay, good question, Blake. T of n here is the number of operations, or the equivalently the time taken to solve an instance of size n. So here, the instance size is just the number of movies. So this takes n squared time if there are n movies. Now, hopefully it's clear that the number of inversions could be up to roughly n squared over 2. If you take if A has the exact opposite preferences to B, then every single pair of indices will be an inversion, and so you'll have about n squared over 2 inversions. And certainly, you can't count those one by one and finish in better than n squared time. So we have to do some method that doesn't count the inversions one by one. So our idea here will be do something pretty similar to merge sort in the end. We're going to count the inversions as we sort the array. So say I have the array. So if you remember a minute or two, I went, oh, I get it now. It's because I realized what some of the confusion here has been. It's basically to do with the indexing being a little weird. Of course, earlier I've defined the indexing kind of in the opposite way to how this usually works. Like if you look at array A in any other context, usually we would define this as little a of, would say capital A of 3 equals 9, not this way around. Yeah. As it happens, it doesn't really matter. Like, so I've taken this same array A and I've how to put it? How to explain this? Yeah, I know. All I'm going to say here is it doesn't actually matter which way around you, like, as if we have like our algorithm just has to handle permutations of the numbers 1 through n. The actual direction of the indexing doesn't matter because we have to handle all the orderings, like any possible ordering, and you could just as easily get one ordering as another. And yeah, like if you reverse the indexing, you just get the inverse permutation, which is itself a permutation. So let me just describe the problem in more stripped back terms. That's the word. I have an array A. I want to count the number of pairs of indices I and j so that I is less than j, I is the earlier index, but AI is the greater value. Okay, so what we're going to do is we're going to split up the array A into 2 equal parts. A low will have the first half of the array, A high will have the second half of the array. And then the inversions within this array can arise in a few different places. You can have an inversion entirely within A low. For example, 9 and 7 are out of order, and both are entirely within A low. In the second half, we have 4 and 2, which are again out of order and entirely within the second half. You can also have inversions across the partition. You can have 7 from the first half and 4 from the second half, which are out of order together. There are many other examples of inversions here. 12 and 7 form an inversion. 1 and 4 do not form an inversion. 4 and 8 do not form an inversion, and so on. Make sense? So we can say that the total number of inversions, I of A, the total number of inversions in the entire array A, is made up of inversions entirely within the left side, inversions entirely within the right side, and inversions crossing the partition, A low, comma, A high. Now, to work out those first two terms, the inversions within A low and the inversions within A high, that's the easy part. We started with an instance of size n, and we broke this down into 2 instances, each of size n over 2. That's the same problem, but just a smaller instance of it. So we can solve those first 2 terms recursively. Yeah, apply the exact same algorithm that you do for the entire array A to the smaller instances, A low and A high. So those also get broken into half and half, and so on. The difficult part is to work out the last term. How many inversions are there that cross the partition? How many inversions take the low example from the first half and the high example from the high term from the second half? Yeah, an example is coming. Don't worry. So, in this case, we have many inversions, but I'm going to focus on all the inversions that involve one particular value from the array. Let's take the number 8 that occurs at the 10th index of the 10th index of the array. I'm just going to focus on inversions crossing the partition because, again, inversions within any half are going to get counted later within the recursive step. So I'm not worried about the inversion. It's the inversion involving the 8 and the 2. That's going to get counted later when I divide further within A high. I'm just worried about inversions between this 8 and things that are from the left half of the array. Values from the left half of the array, values from A low which are less than 8 do not form an inversion with 8. Values from A low which are greater than 8 do form an inversion with 8. So the number of inversions crossing the partition and involving this 8 is simply how many things in A low are greater than 8. Do we agree? In this case, it's 3. The issue is we need to count this systematically. We need to count all the inversions crossing the partition, and we need to count them quickly. So we want some way of counting that there are 5 inversions involving the 3, 5 inversions involving the 4, only 4 inversions involving the 6, 3 inversions involving the 8, and so on. And we want to do this, efficiently. However, whatever efficiently means. We don't yet have a system for doing this. But, any suggestions here? How would you, is there a way to quickly look up how many values in A low are bigger than 8? Yeah, the problem is that right now we're looking for values within A low, and they could be anywhere within A low. There's no structure to A low, so there are 6 items, and any of those 6 could be greater, and any combination of those 6 could be greater. So there isn't really anything better than iterating through all 6 of them. But if it was sorted, then there would be better ways to do this. Certainly, if the left half A low was sorted, then I could, for example, binary search within that to find the position that 8 would go in within A low, and then I could add the number of things to the right of that insertion point. Now, this is a good idea, but we can actually do better. So if you were to do this approach, there are half n items of A high, and for each of those half n items, you're going to do a binary search within A low, which means that to count the number of inversions crossing the partition, you are spending theta of n log n time. Do we agree? Because for each of n over 2 items in the right half, you're doing a binary search of the left half. So that's n log n. However, this is starting to feel very much like merge sort. Yeah? And in merge sort, the merging only took linear time. So let's try and do something very similar to the merging and see if we can actually count the number of inversions crossing the partition in not n log n time, but strictly linear time. Yeah, that's the idea, Hussein. If not just A low is sorted, but also A high is sorted, then the merging algorithm from merge sort kind of does 2 pointers, one through A low and one through A high, and those pointers should let us calculate much even quicker than binary searches. It should let us calculate the number of inversions crossing the partition. Yeah, so a few of you have come up with the same idea, which is not just counting the inversions, but also sorting. So what we're going to assume is we first recurse into the subproblem A low and the subproblem A high, and our function not only counts the number of inversions within those, but it also sorts the two subarrays, the first half and the second half. At this point, we are now going to count and merge as we go. A note here, we are going to count every inversion according to the lesser of its elements. So remember we had inversions involving the 8, where it was 9 and 8, 12 and 8, or 10 and 8. We are going to count those inversions when we get to the 8. We're not going to then count them again when we get to the 9, the 10, or the 12, right? So every time I get to a 9, I'm going to say all its inversions are already accounted for. Let's have a go at this. So the main idea is we've already counted and sorted within a low, counted and sorted within a high. I'm now going to merge them together, and as I merge, I'm going to count how many new inversions I get. Anytime I merge from the left side, nothing happens. So the first thing that I'm going to add is the 1. That 1 goes into the bigger array A, which we're going to make sorted as we go. But that bigger array, sorry, but that doesn't account for any inversions. This 1 isn't the lesser element of any inversion, because if it was the smaller one, then the bigger one would have to be even earlier, which isn't possible. So now that this 1 is written into the merged array, we can grey it out. Next up, the smallest remaining, by again comparing the first active from A low and the first active from A high, so the 5 and the 2 respectively. The 2 wins, and so that 2 is going to get written into the merged array A. And at this point, we're going to count the inversions involving this array 2. How many inversions involve, the number 2? How many inversions crossing the partition involve the number 2? Well, this number 2 should be less than the 5, because that's how we decided to add the 2 now. But also because A low is sorted, everything beyond that 5 is even bigger, which means this 2 forms an inversion with everything remaining in A low. Yeah, it doesn't form an inversion with the 1 because that one went first, but everything else in A low is known to be bigger than 2, and therefore 2 has 2 is responsible for 5 inversions. So we add 5 to our total. Now that we've added 2, we can grey that out and again ask ourselves, which is bigger, 5 or 3? Again, the 3 wins, so it gets written in, and it too has 5 inversions with things from A low. On the next round, the 4 wins against 5, and so it too contributes 5 inversions to the total. Next, we're comparing 5 against 6. 5 is smaller, so we're going to write that 5 in. And here I want to mention that, again, we are not counting any inversions when we do this. Certainly 5 does have some inversions crossing the partition. 5 is in inversion with 2, 3, and 4, but why are we not counting those? Why are we not counting the pairs 5, 2, 5, 3, and 5, 4 at this point? It's because we've counted them already. Yeah, we counted the pair 5, 2 when we wrote when we wrote number 2 into the second slot, so we don't need to double count it now. Yeah, Blake's exactly correct. So we don't add anything to the total here. Next up is comparing 7 and 6. The 6 wins, and therefore it is written into the merged array. This 6 is inversion with everything remaining in A low, of which there are 4 things, so we add 4 to the total. Next up, we're comparing 7 and 8. 7 wins. Comparing 8 and 9. 8 wins. And 8 is inversion with the 3 remaining entries of A low. 9 and 10 get written without further drama. And finally, comparing 11 and 12. The 11 wins, so the 11 is written in. It's in inversion with the 1 remaining item of A low, so we add 1 to the total. And finally, 12 is the last remaining, it just goes in. And so we counted a total of 23 inversions which crossed this partition. Note, this count doesn't include the inversions within A low or within A high. Yeah, those were counted at a deeper level of the recursion. Why not count 5, 6, 5, 8, and 5, 11? Because those are not inversions. Remember, like, inversions are pairs that are out of order. 5, 6 is in order because 5 appears in the first half and 6 appears in the 5 appears in index 2, 6 appears in index 10, and therefore they're not an inversion. They don't count. That pair doesn't count to the total. Yeah. So hope that answers your question, Xiao. This is all well and good, but how do you come up with this? That's a fair point. I think this is difficult to motivate if you haven't seen it already. I'll come back to that. Andrew asks, when we add the first 5 to the total, why is it 5 and not 6? It's because we're counting the number of things that 2 is in inversion with from the left half. That's only the things that are still remaining in A-low. So because the 1's already deactivated, there's only 5 things remaining, and we can look that up in constant time by doing some pointer arithmetic, right? We have pointers to the 5 and the 2, so we can to the numbers 5 and 2 in A-low and A-high respectively. So we can again do some pointer arithmetic to see that there are 5 things remaining in A-low, and therefore we should count 5 towards the total. I hope that answers your question, Andrew. Why do we not add 1 first? 1 was added in the first round. We said which is smaller of 1 and 2, right? Exactly in the same way that you merge things in merge sort. You start with the first element of each. 1 wins, and so 1 is added, but 1 doesn't have any inversions with anyone, right? Because 1 is smaller than everything in A-low. So let me try that again. We're only interested in inversions crossing the partition, right? If 1 is smaller than 2 and A-high is sorted, which means everything later in A-high is even bigger than 2, then certainly 1 isn't going to be out of order with anything in A-high. So we didn't add anything to the total here. Yeah, we're sorting as we go. I hope that answers your question, Andrew. Okay, so yeah, so we are also this is only the inversions that we count at the top level of the recurrence. We also did a similar process as we sorted A-low, because A-low would have been broken into its first half and its back half. Each of those solved, and then we would have some merging required to construct A-low. Yeah, so we split the array in half, we merge sort while counting inversions, and then merge them together. Yeah, exactly. Tuaka, I hope that answers your question. So we're splitting the array in half. We recurse on each half. The product of that recursion is to count everything within each half and sort. Yeah, multitasking is the answer, really. How to put it? We do the counting at the merge step in merge sort. So yeah, we're not doing all of merge sort first. We are recursing on each half to make them sorted, and then at the because merge sort goes recurse on first half, recurse on second half, and merge. Yeah, and all we're doing is as we merge, we're also counting. Make sense? Count 3 and 1 again. Yeah, sure. Yeah, I haven't forgotten the question about motivation for this. I'm going to come back to that. So here we've compared the 7 against the 8. The 7 won, and so the 7 gets written in. Next up, we're comparing an 8 against a 9. The 8 is the smaller of those two, and it's in inversion with the 3 largest elements of A-low, so we add 3 to the total. Next, we're comparing 9 against 11. 9 wins. We're comparing 10 against 11. 10 wins. And finally, we compare 11 against 12. 11 wins, and it's in inversion with the one remaining thing in A low, which is why we add 1 to the total. So see how I hope that explains things? No, not exactly. We are running the merge sort algorithm. So merge sort goes split into the first, how to put it? Merge sort goes recurse on the first half, recurse on the second half, and then merge. In fact, I'm going to pull up the slide for this from last week's lecture. If it lets me. What? Oh no. Okay, I've got some kind of bug. Right, let's recap what merge sort does. If I want to merge sort an array from index L to index R, first I will recurse on the first half. Then I'll recurse on the second half. And finally I'll merge with say this. Yeah? This is how merge sort works. This is this produces array A low, the second step produces array A high, and then the third step is to merge them together. So, again, I split it into the low half, I sort that using merge sort, I also take the high half and I sort that using merge sort, and then I merge them together. The only modification we're making to this algorithm is that as we merge in step 3, we are also counting the inversions that cross the partition. That's the only change we make. Yeah, that's actually it. So the counting takes place as we do the merging. Yeah, so I hope that clarifies. Okay, if it's a miscommunication, that's fine. That's okay. All right. What else do we need to talk about? Lance. Counting the number of inversions of A. Oh yeah. Remember, we defined B to be in order. We defined the labeling of the movies 1 through 12 was precisely according to B's ordering. Yeah. So we defined B as being ordered, so this doesn't come up. Scroll. Okay. All right. Cool. Let's return to the slides. 23 is not the overall number of inversions in the original array A. It's just the number of inversions that get counted at the top level of the recursion tree. Within the counting, the total, the answer itself will be made up of inversions between A low and A high, but also inversions entirely within A low, entirely within A high, and those would get counted at the merging it within the lower levels of the recurrence tree. Okay, I've got a bug here. We are going to keep splitting. Hang on, I've got my slides just stop going. Let me pull this up again. Okay. Sorry about that. Okay, we good. So we are going to keep going. So we start with this original array of 12. we split it into A low and A high of size 6 each. Within that, we split into 2 subarrays of length 3, and we keep going down. We're not really going to worry too much about the split, like the rounding when you split an odd number into two halves. The rounding it's covered in more precisely in the slides, but we are worried about the large scale instances, so this rounding won't affect our complexity, which is what we're really after. So as we merge, so the way that this algorithm executes is that we first go down to merge sort A low. Then within that, it does some stuff and counts sum total, which is the total number of inversions that were counted as we merge these two. This is going to have some inversions. This is going to have some inversions. At each step, I'm just going to count the number of inversions that occurred in the merging step. Then I'm going to go down to A high and do the same, work out the number of inversions that were within A high. And finally, once I've got both A low and A high, those are going to get merged together. And in the process of merging A low and A high, that's when I'm going to count these last 23. Rounding isn't super important. You should mention it. You should mention it if it matters. Like, you don't, like, if you're just doing a standard binary search, you don't need to discuss that. If you're doing something a little more exotic, then you should mention it, but it won't be a great focus of ours. It will be, if it's not something that actually makes a meaningful difference, we won't mark for it either. If it's something that is actually important to the ability of someone to, say, implement your algorithm, then we have to be more careful. I hope that clarifies then. Yeah. Yes, exactly. We do split multiple times, just as in merge sort. We split all the way down. What I've shown in this diagram is the number of inversions that we're counting during the merge step in that topmost split, right? But if I just go all the way back, as I'm counting up, as I'm forming A low, as I'm sorting A low using merge sort, I'm going to count another several inversions here as well, right? Within A low, there are 1, 2, 3 inversions, if I'm not mistaken. And so those 3 inversions would get counted within the lower depths of the recursion tree. The 23 that we're counting is not the overall answer, it's just the number of inversions that cross the partition. It's the number of it's the part that we add to the answer in the topmost node of the recursion tree, but within each other node we will also have potentially some inversions to add there. So in total, I think the answer comes out to 30 inversions. There should be 3 within A low, 4 within A high, and 23 that cross the partition. But those 3 and 4 get counted within further splitting, further recursion trees, like further nodes of the recursion tree. Okay. So I hope this has clarified. This diagram took so long to make. Right. So we mentioned that we were counting each inversion by its greater element, which means that by its lesser element, which means the lesser element always had to come from A high, right? If you're taking an inversion between A low and A high, the lesser of the two has to come from A high. So we don't have to count anything when we get to when we merge something from A low. So overall, what have we done? We've counted the number of inversions within A low and A high recursively. We've also, I've got a double bracket in there. We've also counted the number of inversions across the partition. Adding up those three terms gives me the total. Yeah, and importantly, we have like the modifications that we made to the merging in merge sort still take linear time. To see why this is, every time that I pull something from A high, it only costs me a constant amount of work to find out how many inversions it contributed. So when I pull this 8 from A high, all I have to do is some pointer arithmetic to see how many things from A low are still remaining and add that to the total. That's a constant amount of work done n over 2 times. And therefore the merge, which is taking linear time, has an extra linear amount of work added to it. It's still linear. Yeah. You should hopefully be aware that in merge sort, the important point is that merge step is linear time. Linear meaning big O of n. And so we're adding a further big O of n amount of work to it. So it's still linear. 2n is still big O of n. So we're going to take a break here. We're going to take a break here, and after once we return, we'll be generalizing this method to more kind of recurrences like this, where we divide problem like an instance of size n into smaller instances of not just n over 2, but more, potentially more subproblems, and generalizing the amount of work that we do to split them up and put them back together. The process of counting this quickly is complicated, sure, but the saving between counting this in n log n and counting it the brute force way in n squared is vast. If there's a million movies, counting them in n log n like this on standard mission, like on a typical home computer, will be a second maybe. If there's a million movies and we're doing the n squared way, the brute force that we discussed at the start, this is taking years probably. So there's a vast difference between the two, and so there's some extra work required to design this algorithm, and it's not as easy of an algorithm to communicate or to think of, but it runs so much faster that that's worthwhile. And hopefully it's clear that improvement outweighs almost any change in constant factors. Yeah, we don't care that it's taking 2 times something. 2 times a second is 2 seconds. That difference is negligible compared to years. So that's why we don't care about constant factors. As okay. Yes, it's a good point. We didn't, we are working with arrays A, which are permutations of the numbers 1 through n. But we didn't actually use that property at any point. This array could have just as easily been any n numbers, and therefore we've actually solved the general inversion problem. I want to say not quite, because we haven't dealt with duplicate elements, but there's one extra line required to deal with duplicates, and then it still works. So yeah, absolutely, this can solve the general inversion problem, which is counting the number of out of order items in just any array, not just a permutation array. Are we tested on the reasons why we use the algorithms and how they're derived, or just on which is the most efficient algorithm to use when? I'm not entirely sure what the question is. In almost all circumstances, we're going to prefer the one that has better worst case asymptotic complexity. I hope that answers your question, Wayward. I'm not entirely sure if you were asking someone else. So this algorithm is basically a merge sort which adds constant amount of counting in each iteration. Not exactly. It adds a linear amount of counting in each iteration because for each of linear many items in A high, we do a constant amount of extra work. However, we're already spending linear time to just do the default merge, and so adding an extra linear, adding one linear function to another linear function, the result is still linear. So we are not changing the asymptotic complexity of the algorithm. Now, so again, we're on a break, so if you want to step away for a few minutes, that's completely fine. I guess I can keep talking about the motivation for this, if you'd like. I suppose this is really a generalization of the idea that n binary searches can be replaced with a two pointers kind of sweep. This is a technique that you can that once you learn, you can basically drag and drop into a variety of problems. Break will end at say 5:20. I think we may go like 10 minutes over time, but we'll see. So did I answer that? Yeah. So how would you come up with this? I think some of it you guys came up with already. You already said, "Oh, I'd like to have A low sorted so that I could more efficiently find the number of things involving a particular item of the right hand side." And your familiarity with merge sort would have helped you motivate the idea that we ended up doing, this kind of merge, like count as we merge idea. So there is a large part of getting good at this course, which is just doing a bunch of problems, getting familiar with a whole bunch of different techniques that you've seen in earlier courses as well as new in this course, and doing enough problems that you develop some intuition for when you can drag and drop them into solving other problems. We're also going to come up with a framework that can kind of let you reverse engineer what you're looking for. So since the brute force is n squared, and we're looking to do better than the brute force, n log n is one thing to aim for. And one way of getting an n log n algorithm, as we're going to see, is to split into two halves, each of size n over 2, and spend linear amount of work putting them together, much the same as in merge sort. This can kind of motivate, okay, I can, even if I can't do the whole problem all at once, I can split it into two halves, do whatever, like solve the problem within those two halves, and now I'm just worried about things crossing the midpoint. So later on today, we're going to see the master theorem, which gives you, again, a unified framework for dealing with these kinds of recurrences. And using that master theorem, you can kind of anticipate what term you want at the end, how much time you want to spend on splitting up and recombining, and that's typically the difficult part to motivate. So at least you have a target time complexity for that operation. So, yeah. Not sure entirely what you mean, Wayward, because we haven't actually covered very much new material. In terms of assessment, the assignment questions are pretty typical of the style of problems that you'll be asked. You can also be asked, okay, you have these two algorithms, or these two time complexities, which is most suitable for a particular instance. In most circumstances, it would be the one with better asymptotic complexity, but if one has a very bad constant factor, then it might outweigh that improvement, which again we're going to discuss tomorrow. Over-explaining, not really. We might write you a comment and say, hey, you're trying too hard, like you can make this more concise, but in terms of marking, no, we're not going to. We understand that you're trying to cover all your bases. That's okay. We ask you to write something concise, if at all possible. Yeah. Yeah, like, look, at that, if you're writing 5 pages per question, you are making it like, I can't think what you could possibly write to fill that isn't repeating itself or contradicting itself, because there just isn't that much to write about most of these problems. Yeah, so if you're getting beyond like 2 pages, you really should consider, am I trying too hard? Is there a more concise way of saying the same thing I'm saying? But at the same time, we will do our best to make sense of it. Yeah, Pratik, that can be absolutely fine. In fact, there are some, last term we ran this course with no subparts, just for 20-mark questions, and there were plenty of times when half a page for the entire 20-mark question was fine. So yeah, that's completely okay. Yeah, like for an 11 marks question, a paragraph is probably the minimum, because you not only have to describe an algorithm but also justify the time complexity and the correctness. So yeah, a paragraph is really the minimum that you should be writing. But if you're writing more than a page or two, you should really consider, am I doing this am I explaining myself clearly, right? We won't deduct marks for writing style where we can still understand what's going on. If we can't make sense of what you've said, then we can only mark what's in front of us, right? So yeah, dot points are completely fine. Dot points, subheadings, bullets and numbering, that's all fine. Abhinav, I expect so, but that'll be confirmed in a few weeks' time. Yeah, like, again, I think someone put this well. You should provide enough detail that an intern can implement this without like thinking too hard. Yeah, so in like a language of their choice, say. So you need to communicate the idea, but explain it so that one of your peers could understand it without thinking too much. When I say correctness, I mean justifying correctness, which means giving some reasoning as to why the algorithm works, why the algorithm does what you want it to do. If you're trying to count the number of things, blah blah blah, why does it actually count the thing that you're saying it does? In our case, it would be because every inversion must cross, like in the case that we just did, it would be because every inversion must cross some midpoint if we zoom in enough, right? Because even 2 consecutive entries, eventually they will not be in the same subarray, and so at some point it gets merged, and we count it exactly once. We count it by its lesser value, not its greater value. So this is why it would be correct. Yeah, look, you can write your correctness as you describe the algorithm. That can be fine, or you can do it in a standalone section. It's up to you. Whatever is most natural, whatever makes more sense as you're writing. Sometimes the correctness is not obvious and might require a formal section. It might require a formal proof, in which case you really don't want to do that as you're describing the algorithm. So like if we tried to prove correctness of the stable matching, like the Gauss-Shapley algorithm as we stated it, that would really be a struggle, yeah? So I don't recommend it for every problem, but you may find that in some cases it is more natural to justify correctness as you're explaining the algorithm. Other times it'll be better to do it separately. Okay, I hope that's all making sense. It's break's over, so we should really get going. So we're just going to cover section 2 for the rest of today's lecture. Yeah, description, time complexity, correctness, that's correct. So the rest of today's lecture will be on this section 2, which is a more general framework for dealing with divide and conquer algorithms and their time complexity. Yeah, and up to and including the master theorem. So, why do we care about recurrences? Many divide and conquer algorithms look like start with an instance of size n, split it into several instances, each of size some fraction of what we started with, and then recombine them. And so to estimate the time complexity of such an algorithm, we often get a recurrence that might look something like this. So we started with an array of size n, we've solved each half, so 2 instances each of size n over 2, and then we did some extra work to recombine them. So the runtime for our inversion counting algorithm went t of n, the time taken to solve an instance of size n, was 2 times the time taken to solve an instance of size half n, because we had to solve a low and a high separately, plus some constant times n. The inversion counting is linear in n. And many divide and conquer algorithms can have their time complexity analyzed in the same way. You have several instances, several smaller instances, each of size n over something, plus some extra work to recombine. So in general, we might have this kind of framework. A divide and conquer algorithm starting with a problem of size n and reducing it to a many problems, each of size n over b. We also have some overhead to split up the problem and to recombine those solutions. So this includes both the splitting into halves or whatever fraction, plus the work required to put back together the solutions to the smaller part in order to solve the bigger original subproblem. Then the time complexity of this algorithm would be to solve an instance of size n, we need to take a times the time taken to solve an instance of size n over b, plus a further fn to recombine. Does that framework make sense? Importantly, the a and the b aren't always the same. We've already seen a couple of examples, merge sort and inversion counting, where both a and b were 2. We divided an instance of size n into 2 halves. Can someone give me an example of a divide and conquer algorithm that you've seen before where the a and the b here are not the same? There's a fairly elementary divide and conquer algorithm which has this property. What's the first divide and conquer algorithm that you learn, I guess? And the most useful, I think. Yeah, binary search. A here is the number of small subproblems. B here is the fraction that the small subproblem is as in terms of the size of the original one. So binary search here has A equals 1 and B equals 2. You start with an instance of size n, and you split it up into one instance of size n over 2, plus a constant amount of work to split up and recombine. Yeah, you're testing the midpoint should take constant time, and then you recurse only on one side. So it takes one, you reduce your instance from one instance of size n into just one instance of size n over 2. Quicksort is an interesting case which we're going to discuss tomorrow. Yeah, that's true. When you throw away parts, A would be less than B. But you can also have instances where A is greater than B. This is also possible. So matrix multiplication using the Strassen algorithm is an example of this. But that's complicated, so we won't show it here. That is something that we can that you can look into. In fact, we might even write something on the forum about that. But yeah, as a general kind of example, you might have matrices of size n by n. So Tn will describe a matrix of size n by n, But of course I can divide this into some submatrices, and maybe I do some algorithm which takes my original matrix and splits it into all 4 of these submatrices, does some work on each of them, and then recombines. I'll be recursing on 4 instances, each of size n over 2, because they're n over 2 by n over 2 size matrices, plus f of n. Yeah. And so in this kind of situation, A is greater than B, but you're not throwing away any parts. In fact, you're not even having any redundancy. You're not having overlapping parts. So there's it kind of, how to put it? What I'm saying is that this framework is useful in a wide variety of contexts. Yeah. So when you're doing matrix multiplication using the Strassen algorithm, this 4 gets replaced by a 7. So you can multiply n by n matrices using 7 multiplications of n over 2 by n over 2 matrices. But again, that's something that we're going to approach. We're not actually going to see it. We're going to approach that tomorrow. For now, I want to just return to this kind of instance. We're splitting up our big problem of size n into many problems, each of size n over b, some fraction of the original. And the number of such subproblems is a, and f is the amount of extra work that I do to recombine those, to split up and recombine those. Yeah, so, and you'll notice here that b doesn't even have to be an integer necessarily. You can do things like there's a version of like ternary search where you divide by golden ratio, and so there b would be phi, the golden ratio. So yeah, we can analyze a wide variety of these, a wide class of divide and conquer algorithms using this same framework for recurrences. Now let's move on. Before we do that, I do need to address some of the rounding issues and so on, and I'm going to address those by saying it doesn't matter. So when we divide our instance of size n into smaller parts, then we do need to round up on those sizes, but again, that rounding makes no difference in the long run. So when we talk about the asymptotic complexity, we can safely ignore these. We can safely ignore rounding and any additive constants. So n over b plus c, we don't care about the c. It's not going to make a difference. So, okay, we're not doing 1.5 of a problem. 1.5 of a problem would be doing 1.5 many problems of the same size. So taking a equals 1.5, yeah, that doesn't make sense. A has to be an integer. But we can do problems of size, not 1.5, but rounded up. Yeah, if I start with an instance of size 10 and I make it into instances of size 10 over root 2, then my new instance would be size 8, I think, if I'm not mistaken, because it's like 7 point something, right? So generally we'll round up, but the rounding doesn't matter. The rounding doesn't affect the asymptotics. So here's kind of the recursion tree that we're dealing with. We start with instance of size n. We split it up into a many instances, each of size n over b. Each of those is split up into smaller instances that are smaller still. N over b, then divided by b again. So there'll be each of those a fans out to another a of size n over b squared. Then those fan out into n over b cubes, and so on, until eventually the instances become trivial. Once the instance size is 1, say, there's no recurring further from that. You stop, and therefore the depth of the recursion is how many times can I start from n and divide by b, divide by b, divide by b. How many times do I divide by b to get from n to 1? That's exactly what log base b of n means. Alright. So far so good. Now, actually solving for T of n, finding a closed form solution for T of n is sometimes possible but usually difficult and not our focus. Remember, actually giving a concrete value for the amount of time that some algorithm takes is a bit tricky and doesn't always tell us the full story. We're more interested in the asymptotics, and fortunately, the asymptotic solution of such recurrences is much simpler. We have a well-known way of doing this. So we don't need the exact solution, we only need the recurrence. We only need the growth rate, that is the asymptotic behavior. We also do need to have some kind of handle on how big the constants are getting, but we'll discuss that tomorrow. For now, just worry about the asymptotics. So the master theorem is going to be important for finding the asymptotic solution to these recurrences. So here we're gonna see some maths. So the setup, I've got a double and. The setup is going to be the same. Fn is going to be the function that defines how much work we take to split up a large instance into several small instances, as well as the amount of work to recombine those the solutions to the small instances to make a solution to the big instance. So this is going from the sorted A low and the sorted A high to the sorted A together with the count. Yeah, so in our earlier example, Fn was some linear function. Tn is going to be the time taken to solve an instance of size n, and it's going to obey this recurrence as before. And so we're going to need some definitions. First, we're going to define C star as log base b of a. So b and a are these constants, b being the fraction by which our smaller instances are compared to the original one, and a is the number of small instances we make. So C star will be defined as log base b of a. The critical polynomial will then just be n to that power. Again, in any situation like this, a and b would be given constants, and we're trying to, as well as f would be some known function, or at least we'd know the asymptotics of f, and we're trying to solve asymptotically for t. This critical exponent is going to be important because it's going to classify these recurrences into a few different cases. So let's start with the first case. In case 1 of the master theorem, our given function f of n, our splitting up and recombining work, is big O of a power smaller than the critical exponent. In this situation, then the amount of work taken to solve the original problem is exactly big theta of the critical polynomial. That is the asymptotic solution to the recurrence. Yeah. Again, C star encodes some is in terms of B and A, so this is involving all the variables that we were given, but it is as simple as this. If Fn is dominated by the critical polynomial, if there's some separation in the index, then we can solve the recurrence. Furthermore, if Fn is exactly big theta of the critical polynomial, then our solution is similar. It's the critical polynomial times an extra log factor. The third case is a little more complicated. Here we go the other way. Fn, the amount of work taken to split up and recombine, is big omega, so it dominates the critical polynomial plus a little bit. And also this inequality holds, then the solution to our recurrence asymptotically is just the amount of work to split up and recombine. So as a summary, the first case is really describing those situations where the amount of work to split up and recombine is relatively small, and the amount of work to... Sorry, just a minute. Sorry, has some visitors at home, and my room's pretty close to the front door. Okay, let me try that again. Fn, so yeah, not dog on this case. In this case, so the first case is where Fn, the amount of work to split up and recombine, is small. It's dominated by the fanning out. The number of subproblems contributes more to the to the total time taken than the actual individual bits of splitting up and recombine. In the second case, they kind of contribute equally in some sense. And in the third case, the amount of work to split up and recombine at each step is quite large, whereas the fanning out is not as extreme. But again, we're going to do some examples of this. So, this slide is more for reference than anything. It's a reference for you to come back to afterwards. We're going to do some examples which show you, why this matters and how we use it. There's a lot of maths here that I don't want you to hyper focus on. We're going to see actual examples of this, and it's going to be much less intimidating than what we've got on the slide right now, I promise. On the other hand, you might observe that case 3 is a little more complicated than the others. It can actually be simplified. So, as an exercise, you can prove that the two conditions for case 3 are actually only one condition. Only the second one matters, because once you have that second one, then the big omega statement follows as a consequence. Now, if none of these conditions hold, if it's not in this big O, big theta, or big omega case, then we're not going to apply the Master theorem to it. However, often the same techniques that we use in the proof, which we're going to see in a bit, work the same. Now, I want to, there's a lot of maths here. Don't worry about it for now. We're going to come back to it. We're going to see some examples and return to this. I want to mention here that elsewhere on the internet and so on, you'll see some versions of the Master theorem which expand on this, which throw a few more things into case 2, not just things that are exactly big theta of n to the c star. For the purposes of this course, you should follow what we've done in the published lecture materials. You can look into those if you'd like. We're not going to focus on those, but basically some of the things that we classify as case 4, not having the Master theorem apply, some of those fall into the case 2 according to other sources. Now, before we get started doing some examples and looking through the proof of this, we're going to need some preliminaries again. So here we're going to recall the logarithms that we talked about last week. Remember the very important statement that the base of the log doesn't matter. We said that log base a of n and log base b of n are only different by a constant factor, namely log base b of a, and therefore the log doesn't matter. We can rather than saying fn is log base a of n, is big theta of log base a of n specifically, we just say log n. All the bases are the same for our purposes. But there's a very important disclaimer to this. This only applies to kind of bare log terms, or log terms times some other stuff. It doesn't apply when the log is in a power. So you've seen here that often we have terms like n to the c star, and you might remember c star was defined as log base b of a. Here we can't just suppress the b in that base, because the log appears in a power, and it's no longer the case that n to the log base a of x and n to the log base b of x are interchangeable. That's not true. Yeah? So anytime that a log appears in a power, the base is really important. Anytime the log appears just as a bare term, then the log can be omitted. Then the base can be omitted. All right? Because changing the constant from n squared to n cubed makes a difference. Changing the constant from 2 to 3 does not. All right, let's do some examples where hopefully we'll get an idea of what the Master theorem does, how it can be applied, and how to write up solutions to these recurrences using the Master theorem. And hopefully you'll see that it's really not that intimidating. The amount of maths required is not that important. Yeah, it's basically like that. You are not just changing a constant anymore. You're not just changing a constant multiple. You're changing the index, and so you're changing the index by a constant, and that makes a significant difference. So, example 1. Here we have the recurrence Tn equals 4 times Tn over 2 plus n. So we're going to always start these by picking out the a, the b, and the f of n. So a is 4, b is 2, which means that we can work out our critical exponent. The critical exponent was log base b of a, b was 2, a was 4, so we have log base 2 of 4, that is 2. So the critical exponent C star is 2. Remember, that's going to be important for classifying which of the 3, or indeed 4 cases this falls into. We're also going to care about the critical polynomial n to the C star. So let's keep in mind that that is n squared. And now, recall that what we had to do was compare the function fn, the last term, to things like n to the C star. Really what we're asking here is, this last term fn is n, is that much less than n squared? Is it asymptotically the same as n squared? Or is it much greater than n squared? In this case, it's obviously much less. And to make this formal, we can say that fn is big O of n to the 2 minus epsilon for some small epsilon that we choose. 0.1 works fine. Yeah. Certainly if I pick epsilon equals 0.1, then I have a power of n, namely n to the 1.9, which is less than the critical exponent, but still dominates my my last term f of n. So a power of n that is smaller than the critical polynomial, but still dominates the f of n term. This is what we need to be in case 1 of the master theorem. And it is as simple as saying, in case 1 of the master theorem, the asymptotic solution to the recurrence is just Tn equals big theta of the critical polynomial, in this case n squared. Yeah. So by identifying the a, the b, and the fn, working out the critical polynomial, and using the critical polynomial compared to the fn to classify this recurrence into one of the 4 cases, we were able to write out the solution. We were able to write out the asymptotic solution to this recurrence without knowing any of the details of how this algorithm works, or having to do any complicated maths here, right? All we had to observe is there's some exponent, in this case 2, which is strictly bigger than the exponent in my fn, which was 1, so much so that it was separated by enough that I could pick something in between. 1.9 works fine, and at that point I can write down the solution. I can write down the answer to the problem. This is so. For now, it is. We're going to see a couple of examples where it's less so, but for now, yeah, definitely. So next up, we're going to do an example where we split into 2 halves, and we do an extra 5n amount of work. You should recognize this as being basically what we've done for inversion counting and for merge sort. Split into 2 halves and do linear extra work. We hope that the answer is big theta of n log n, but let's confirm that. Again, we're going to pick out the critical exponent. In this case, b and a are both 2, so the critical exponent is log base 2 of 2, which is 1. So the critical polynomial is n. At this point, we should compare the last term, 5n, against the critical polynomial, n, and which relationship does it have? Is fn smaller, like considerably smaller than the critical polynomial? Is it asymptotically the same, or is it much bigger? Of course, in this case, it's asymptotically the same. In other words, we are in case 2 of the master theorem. Of course, fn is big theta of the critical polynomial n, and this means case 2 of the master theorem says the answer is Tn equals the critical polynomial n times an extra factor of log n. And that's it. Does that make sense? Now, this third example is going to be a little more complicated, because here we have a equals 3 and b equals 4. As we compute the critical exponent. C star is log base 4 of 3, which is about 0.8. So I'm going to talk about the epsilon later. All right. The epsilon basically guarantees that there's some actual separation between the fn and the critical polynomial, not just differing by like a log factor, for example. So we're going to come back to that. Remind me if I don't. I'll talk about it in example 4. Okay. So in this case, the critical exponent is about 0.8, and we should compare our function last term fn equals n to the critical polynomial n to the about 0.8 or so. Of course, in this case, fn dominates the critical polynomial, which means we think we're in case 3. Yeah, we're not in case 1 where the critical polynomial dominates f. We're not in case 2 where they're asymptotically equal. But remember that case 3 had 2 conditions. We needed the critical polynomial to be dominated by fn, but also we needed this other inequality. So certainly the first part holds up. N is big omega of n to the power of the critical exponent plus a little bit. Yeah? Even if I add a 0.1 to that critical exponent, I still get something that's a bit less than 0.9. And n is certainly big omega of n to the 0.9 because it's a strictly larger power. We also need to confirm this inequality. If I just flip back for a sec, we need to confirm that there's some choice of c less than 1 and n naught, so that for all... sorry, let me try that again. We also need to confirm that there's some constant less than 1, so that for all sufficiently large n, inequality 1 holds. A times f of n over b is less than or equal to c times fn. There's proof of this, but it is we'll mention it later where that arises from. For now, just take that for granted that this is a thing that you need to confirm. This is the other criterion for case 3, and it's just being told to us by divine inspiration. We'll come back to it. So in this case, we need to confirm that a times f of n over b is less than c times fn for some choice of c less than 1, and we only need that inequality to hold up for sufficiently large n. But in this case, it's quite easy to make that true. A is 3 and b is 4, so the left-hand side is simply 3 times f of n over 4, or 3 times n over 4, 3/4 of n. The right-hand side is c times f of n. And again, f of n is n itself, so this is c times n. We're reduced to asking, is 3/4 of n less than c of n, where we get to choose c, as long as we choose something less than 1, and the inequality only has to hold for large enough n. Of course, if I choose some c that's strictly between 3/4 and 1, say 0.9, then this works not only for n greater than, say, 100, but we could start our n naught as small as we like. So we've now confirmed both criteria for case 3. We've confirmed the big omega condition and the other inequality, and therefore we are in case 3 of the master theorem. In case 3 of the master theorem, the answer is the asymptotic complexity of the original algorithm is Tn equals big theta of Fn, the last term, and that is just n. So in fact, an algorithm which divides an instance of size n into 3 instances of size n over 4 and then does an extra linear amount of work takes only linear time. In other words, the amount of time taken to split up and recombine dominates the time taken to do all the other stuff. All the other recursion stuff is negligible compared to the amount of work required to just do that last kind of merging step. Yeah? So that's the kind of distinction between the 3 cases. Any questions about case 3 before we move on? So about case 3 of the master theorem and indeed this example. So to recap, in example 1, the fanning out of the recurrence was much more important than the time taken to recombine. The fanning out it fanned out quite widely because it fanned out into 4 half ends, and so each of those half ends are going to fan into 4 more, and that spread out so quickly that it was more important to keep track of the number of subproblems that we were making in this way than the extra amount of work that we were doing to recombine the answers. Our recursion tree was very wide in that sense. In this case, both parts are of significance. Neither part is negligible. But in example 3, the recurrence tree was relatively narrow. We only had 3 directions of fanning out, and we were reducing our instance size by 4, and so the recurrence tree is pretty narrow, whereas the n time taken to put everything back together is the dominant term of the complexity. In this last case, would it not be worth it to do divide and conquer? No, not at all. That's I understand where the question comes from, but the algorithm we're doing is still a divide and conquer algorithm. It might be the case, and it typically is the case, that the only reason we're able to do that recombining step in n time is because we're doing something clever within those smaller subproblems. And so, the divide, even though the last step is the part that contributes the most time to the answer, it's precisely because we're doing the divide and conquer part that maybe we're able to do the entire algorithm. So exactly, yeah, we can't really say it without seeing alternatives as well. Yes, significance meaning here what takes up more time. So in what parts are not negligible? What parts are not massively outweighed by the other parts of the algorithm? Yeah. In example 2, both parts, the splitting up and recursion part of it, and also the recombining, both parts contributed significantly to the answer, which is, I'm being vague on purpose because I don't want to get into the depths of it. But yeah, both parts are of significance here, whereas in the other 2 cases, one dominated the other. Okay, let's talk about example 4, and this one is a pretty natural example to come across. Here we divide. In fact, it's the exact example that some of you proposed earlier, which was to not do the 2 pointers merging, but the binary searches. Yeah. So here we do n. We start with an instance of size n, split it into 2 halves of size n over 2, and then do an extra n log n amount of work to put it back together. This appears like it might. This looks very similar to the example 2, right, where the last term was linear and the answer overall was n log n. But we're going to see that this one doesn't fall so neatly into really any of the examples. We'll use the same framework. A and B are both 2, so the critical exponent is 1, and the critical polynomial is n. So therefore, to classify this, we're going to compare n log n with n. Which of those dominates? Which of those is what's the Landau notation kind of relationship between n log n and n? Well, certainly the n isn't bigger, right? I can rule out case 1 where the f part is dominated by n. That's not true. And I can also rule out case 2 where they're equal in asymptotic complexity. That's also not true. Fn, which is n log n, does beat out the critical polynomial here. So Fn, which is n log n, grows asymptotically strictly faster than n. That's what little omega means. Asymptotically strictly faster. It's not bounded above by any constant multiple of n. Which means that both case 1 and 2 are impossible. Yeah? Fn, the last term, isn't dominated by the critical polynomial, nor is it asymptotically equivalent to the critical polynomial. Which means we're only really concerned with case 3. But there also we're going to have a problem. in case 3, you required Fn to be big omega of not the critical polynomial, but something slightly bigger. It was critical polynomial plus, like critical exponent plus an extra epsilon. And that's where we're going to have the complication. No matter how small of an epsilon we pick to add to the critical exponent 1, as soon as we go from n to the power of 1 plus a little bit, now it doesn't work anymore. Fn is not bounded below by this. Yeah? So Fn is bounded below by n, in fact strictly so, but it's not bounded below, asymptotically, by n to the power of 1 plus anything. And therefore we're not in any of the 3 cases of the master theorem. We're kind of between case 2 and 3 in some sense. Yeah? We are strictly faster than the critical polynomial, but not faster than the critical polynomial plus a little bit. So, does that make sense? Yeah? Again, this is what I meant by some sources will present a slightly expanded version of the master theorem, where cases like this get covered under case 2. We're not going to do that because it would complicate the proof that we're about to see. But as an exercise, you can go and prove this. So you can prove that, so as an exercise, prove the big omega statement on the previous slide. It will make use of L'Hopital's rule. Okay? Now, we are going to keep going and we're going to go through the proof, but I want to say at this point that the proof is as close to extension content as can be. If you don't follow any of this, any of the rest of this lecture, you're going to be fine, except for the top couple of students might want to be aware of this. Okay, so if you get it, great. If you don't get it or don't want to stick around for the proof, don't worry about it at all. Not a big deal. If knowledge of this proof is required, it will only be in the hardest question that you see in the entire course. All right. So let's have a look at where the master theorem comes from, and the proof will kind of follow from that. So suppose we have this recurrence. The way that we derive the master theorem is to basically unwind the recurrence. We're splitting this instance of size n into several instances, each of smaller size n over b, but those also get split up into smaller instances of size n over b squared. So the time taken to solve each of those small instances is a times the time taken to solve an n over b squared instance plus the time taken to recombine them. And the size that we're working with there is n over b. So I can substitute that equation back into the previous one, and now I can write Tn in terms of not Tn over b, but T of n over b squared. Of course, the remaining terms are a little more complicated. There's 2 f terms, but we're going to deal with that. But of course, why stop there? Those n over b squared terms, those kind of grandchildren, will be split into themselves yet smaller subproblems. Those will be split into problems of size n over b cubed. Yeah, so if we reduce that term using the same recurrence equation that we saw before, T of n over b squared is a times the time taken to solve a great grandchild instance, n over b cubed, plus the time taken to recombine them, which is f of n over b squared. I can again sub this into the original equation 4, and now I can write Tn in terms of n over b cubed. And hopefully you're starting to see a pattern form here, right? We have n over b cubed, we have a cubed of those, because at each generation we span out in a directions, and then a directions times that, times a directions again. So there should be a cubed many great-grandchildren. We also have to deal with the amount of work to recombine. So for each of the grandchildren, we have to recombine to a size of n over b squared, and there are a squared many grandchildren. For each of the children, there's n over b total size, so f of n over b time taken to split up and recombine for the children, and there are a children, and finally the top level was fn itself. Okay. Sorry. So hopefully you can see a pattern emerging. And as Tuaka says, there's a geometric sequence happening. Kind of. Yeah, so it's not exactly a geometric sequence because the f term is different. But if we assume so far we haven't assumed anything about f, right? But in each case of the master theorem, we know something about the asymptotics of f, and that's going to let us use exactly what you've mentioned, properties of geometric series. Yeah, so you guys have the right idea, like both of you. So if we continue to break down this way, replacing those great-grandchildren with great-great-grandchildren and so on, we'll end up with Tn equals, after we go down k many levels, we'll have a to the k amount of subproblems of that size, and then for each level working up, we'll have the amount of work to recombine at that level, which I can condense using sigma notation like so. How far down do we go? Do we recurse forever? No, we only recurse until we get down to trivial instances, which is when n over b to the k is 1. At that point, there's no point recursing further. So this is going to continue until n over b to the k is about 1. In other words, k is about log base b of b. Log base b of n. Yeah, again, recalling the definition of logs, this is what we want. So, substituting that in, substituting that value of k, and ignoring the floor function in parts, we'll end up with this kind of recurrence. We'll see that the original time taken Tn will be a to the k, where k is that value, times t of n over b to the k, where again k is that value. We're going to see that fraction simplify very quickly. And also we're going to sub in k into the top limit of our sum. And again, this is only an approximation because we're throwing away the floor function, so there is a little bit of rounding and so on, but not in a way that is going to affect the asymptotic complexity. So we're not fussed about the imprecision there. Now, how can we simplify this? Well, the first part is quite nice. Here we have a to the power of log base b of n, and here there's an identity which lets us basically switch the position of the n and the a. As an exercise, prove this. Prove that this identity is true, and we can swap the a and the n. So in fact, this is n to the power of log base b of a. Because again, n is our variable. I'd like to have the that term expressed as a power of n rather than with n in the argument of a log and an exponential. And at this point, this should be ringing some bells. Where have I seen n to the power of log base b of a before? What's log base b of a? Where have you seen that expression? Like a few minutes ago. This was the definition of something. This was the definition of the critical exponent. This was C star. That's okay if you've forgotten. There's a lot going on, I know. And it's quite late. But that log base b of a is C star. It's the critical exponent. And so this entire time, it was a very valid question for you to have. Where have you got this C star from, and why does it matter? This is why it matters. It's because after a bunch of mathematics, bunch of manipulation, it just pops out. So unfortunately, I don't have a great justification for you ahead of time, but hopefully now you believe me. All right. So this critical exponent is going to turn out to be really important. The next term that we can simplify is that fraction n over b to the log base b of n. What is b to the power of log base b of n? This is saying, So log base b of n is asking what power do I have to raise b to get back n. If I then go and do that, if I raise b to that power, I do indeed get back n. So I have n over n, which is 1. Alright? So in fact, this entire first term that I got by breaking down into trivial subproblems is simply n to the power of log base b of a times t of 1, and t of 1 is a constant. So in fact, this n to the power of log base b of a is the first term. And in a way, you can think of this as basically counting the number of subproblems like the number of leaf subproblems, if that makes sense. You started with n many subproblems, and you broke that down in a directions, then a squared, then a cubed, and after you go down until you can't anymore, this is a to the power of log base b of n, and each of those trivial subproblems is solved in constant time. So this is the amount of work required to solve the leaves. And the number of leaves is the important part in this, because each leaf is solved in constant time. The number of leaves, a to the power of log base b of n, can be rearranged as n, as exactly the critical polynomial. So yeah, no, the epsilon is elsewhere. Yeah. Oh, chat is not playing. Okay, that's strange. Yeah, this first term, in fact, the critical polynomial is exactly a good approximation for the number of leaves. Now, throughout this, I am playing a bit fast and loose with approximations. I'll ask you to mainly just take my word for it that these little rounding errors don't affect the asymptotics. That's not where the epsilon comes in. The epsilon is separate, which I'll mention at least in vague terms later on. But yeah, the approximations are only rounding errors. They're not enough to change the asymptotics, so it's fine. And we much prefer to work with these simplified expressions without floor functions everywhere. Okay. At this point, we've simplified the first term. We've said that the solution to this recurrence is the critical polynomial times a constant t of 1 plus this sum s. And this sum s depends on a and b, and as well as the top limit of the sum, log base b of n. However, just to work on this sum in general is pretty much impossible because you don't know anything about f. You can't really work with this as a geometric series because f could be anything. But this is where the three cases of the master theorem giving you assumptions about f, this is where this comes into play. So what we're going to do is we're just going to focus on case 2, which is the simplest one. Here fn is big theta of the critical polynomial. And so we're going to work on that case only, and we're going to give a brief overview of how the other cases are done. So in this case, fn is big theta of the critical polynomial. We're interested in this sum s. So we can replace f with big theta of that critical polynomial. And here we're just going to manipulate some more. So because big thetas respect sums and scalar multiples, I can basically shove everything inside the big theta. Like I have a sum where every term is a power of a times a big theta expression. I can move those a's inside, and I can move the sum inside the big theta as well. Yeah. So this is just using the basic properties of big theta, the sum property, and the scalar multiple property. So now I'm interested in this summation, which is all inside a big theta. The first step is to recognize that in that fraction, I have n to the power of log base b of a over b to the I to the power of log base b of a. That n to the power of log base b of a, no part of that involves an I. Yeah? So in every term of the sum, as I iterates from 0 through log base b of n minus 1, that n to the power of log base b of a is a common factor in every single term, and so I can factorize that out the front, which leaves just a 1 on the top of the fraction. And since both terms that remain inside this sum, both terms are ith powers of stuff, I can rearrange the powers accordingly. I can write everything as an ith power of something. Do we need to know those properties? Yeah, all I've really done is use the properties that use the sum and scalar multiple properties that I presented in last Friday's lecture, but just iterated. So if I have two big theta statements, I can add them up. In the same way, if I have n big theta statements, I can add them up. That's all I've done here. Again, this proof is as close to extension content as they gets, right? Alright, so at this point, I'm left with this sum, but you should notice something about the sum. Particularly, you should notice that the denominator of that fraction has some structure that should look familiar to us. B to the power of log base b of something. Remember, those two operations undo each other, right? Just like we saw to simplify down to tier 1 earlier. In fact, b to the log base b of a is just a itself. So that's a over a. And lo and behold, every single term of that sum is just constant 1. Which means that to find that sum, we just count the number of terms. Yeah? So, after doing a bunch of nice maths, we get down to this sum s being big theta, so asymptotically equivalent to critical polynomial times log base b of n. Not worried about the floor function because, again, who cares about rounding? And also, the base b part of this isn't important either, right? It's just a bare log term. I don't care about what base it is. They're all equivalent. So in fact, the first term is the critical polynomial times the constant. The second term of Tn is the critical polynomial times an extra log factor. The second term of those is larger, and therefore Tn is big theta of critical polynomial times log n, and this was exactly what we claimed in the statement of part 2 of case 2 of the master theorem. So if Fn is big theta of the critical polynomial, then it turns out that the runtime of the divide and conquer algorithm, Tn, is big theta of critical polynomial times an extra log. And we have just proven that. Again, I know there was a lot behind that proof, a lot of steps involved. By all means, take your time if you'd like to understand that, but also don't stress about the proof. It's not the focus of this. You should, as long as you understand those 4 examples and how to use them, like how to use the master theorem in that way, that's sufficient. This is really extension. Okay? Now, as a brief discussion, in case 1, the proofs are not included, but I'm going to give you an outline, okay? To prove case 1, you do something quite similar. So rather than having exactly big theta of the critical polynomial, you're going to have big O of critical polynomial minus a little bit, minus an epsilon. Yeah. The big O still respects addition and scalar multiples. So those first couple of steps of the simplification will be quite similar. The complication is that you no longer have exact cancellation. Like the top and bottom don't exactly cancel because there's this extra epsilon term that only applies to the b parts. But this is okay because we no longer have a sum of 1s. We now have a sum of b to the 1 plus b to the epsilon plus b to the 2 epsilon plus b to the 3 epsilon and so on. That's a geometric series. You can add that up and now the solution falls out. Case 3 is more complicated. Here you have to prove, the aim of the proof is to prove that Tn is big theta of Fn. That's the conclusion that we're aiming for. So we need to prove 2 parts of this. First, we need to prove that Tn is bounded below by Fn. This is obvious because Tn is made up of Fn plus some stuff. So of course it's bounded below by Fn. The other direction is the difficult part. How to prove that Tn is big O of Fn. If you'd like to have a go at this, and again, I cannot stress enough, this is an exercise for top students who are bored with what we're doing so far. If you'd like some extension work to work on, absolutely you can do this. I've given you a couple of hints as to how you might go about this. Okay, so you can read through that in your own time if you'd like to have a go at this exercise, but it is an extension exercise. Okay, and that's all we have for today. 17 minutes over. Okay. Yeah. All right. Happy to take any questions before we wrap up. Otherwise, we will leave it there, and we'll come back tomorrow. Is the closed form of the geometric series with respect to K? It's the latter. It's theta of r to the K. The reason is, like, if K is the variable in this equation, right, and like in the left hand side, you can't simply say that the last term is the biggest and therefore it's the only one that matters. In fact, all the other terms do contribute a little bit, and together they contribute enough that it actually bumps the power up by 1. The reason being that on the right hand side, if K is the variable, then r minus 1 in the denominator is constant, so I can ignore it. The minus 1 in the top is also constant, and so indeed it is r to the K that's important. Yeah. Although, wait, hang on, what am I saying? They're the same, because r to the K minus 1 is just r to the K divided by r, and r is constant. So, who cares? Sorry, I blanked out there. I hope that answers your question, Hussein. Those are the same. Those are the same equivalence class. Yes. Okay, right. I'm glad to know that someone liked it. Again, the proof is the last thing that you need to worry about here. Much more important is to understand that we now have a framework for analyzing the time complexity of divide and conquer algorithms, which follow this kind of framework, which divide a big instance into several small instances of roughly equal size, and then do some extra work to split up and recombine. Any divide and conquer algorithm following that kind of template can be analyzed using these tools. Yes, Red, that's correct. If you go and do example 4 in full, you will end up with the solution you've claimed. Tn will be big theta of n log squared n, but it does require a little bit more work to prove, because what you'll end up doing to solve that is to basically do the proof, like simulate this proof, but like you'll end up simulating this proof, but you'll no longer have that it's exactly big theta of the critical polynomial. You'll have an extra log in there, but you do the same steps. Hussein, how would the proof be assessed? It's almost not assessed ever. The only way that the proof is assessed is basically exactly what Red is asking about. So if you developed an algorithm where you split up into 2 halves and then you did an extra n log n work to recombine, how do you analyze the time complexity of this? Well, this doesn't fall into any of the cases of the master theorem, and therefore to justify that, to actually solve for Tn asymptotically, you would have to go through not the proof in full generality, but the same steps as the proof that we've presented here. In that way, you would indeed arrive at the solution that Red's talked about. But other than that, which again would be something that we expect of only a handful of students, you do not need to actually worry about this proof. However, it's also a very nice mathematical curiosity. I come from a maths background, so I am fully aware that my preferences might be different to other people, but I find it quite nice that everything works, everything falls out exactly as you'd hope it would, right? all those constants that we identified earlier were going to be important. Those ones came back exactly to those showed up in exactly the right places. How to transfer the proved case to big theta to big O. So if you have a big O in the statements that are on this slide that I'm sharing right now, the same statements work. So I can kick the a to the I, which is a scalar multiple. I can kick that inside, and I can kick the sum inside, because big theta, big O, big omega, these all respect the sum and scalar multiple properties in the same way. Yeah, so I'll leave that as an exercise if you want to do it, but again, I want to reiterate, it's really not core material. It's like as close to extension as can be. It's very firmly in the H side of the K and H dichotomy of tutorial questions. All right, I think that should conclude it then. I hope I've tied up all the loose ends for now, and then tomorrow, to give you a preview of what we're going to do tomorrow, we're going to go back to basics and talk about how to add and multiply numbers. So we're going to talk about multiplying numbers, multiplying large numbers, so n-bit numbers. And talk about a slow way of doing it and then a fast way of doing it. And then we're going to talk about quicksort. Yeah, absolutely. Like, I'll show you. We're going to actually do this. All right. So we're then going to spend some time. The majority of tomorrow's lecture will be on quicksort and quickselect. So quicksort you already know about, but you know that quicksort runs in n log n in all but the worst case, and that rare worst case is n squared. We're going to see how to improve that worst case, and also we're going to do the selection problem, which is pick out the kth smallest number from an array. We're going to do that in linear time as well. Okay, let's call it there. So thank you very much, and I will see you I'll see you tomorrow. Tomorrow morning. Yeah, consult tomorrow after that as well. All right. Cheers. See you. Bye bye.